Welcome students, welcome to the series of lectures on matrices and determinants. In the last few lectures, we were trying to solve a system of linear equations by reducing it to its row reduced echelon form. In this lecture, we will see some more problems on solving a system of linear equations and problems based on it. So, let us start with the problem. Solve the system a plus b equal to 8, a plus c equal to 13, b plus d equal to 8 and c minus d equal to 5. Solution. As usual, let us first write down the matrix form 1 1 0 0 1 0 1 0 0 1 0 1 0 0 1 minus 1, and this acts on the unknown vector or the unknowns a b c d. We will get the constant term matrix which is 8 13 8 and 5. Let us write down the augmented matrix of this 1 1 0 0 augmented with 8 1 0 1 0 0 1 0 1 0 0 1 minus 1 augmented with 8 13 8 and 5. Now, let us try to convert this into its RRE. So, only the coefficient matrix part. So, the first row, the first element is 1. So, let us not bother about it. So, we will have to convert this other element which is 1, which is in the second row, into 0. So, R 2 is replaced by R 2 minus R 1. So, the resulting matrix is, the first row remains unchanged 1 1 0 0 augmented with 8. Second row, it is R 2 minus R 1, 1 minus 1 which is 0, 0 minus 1 you will get minus 1, 1 minus 0 which is 1, 0 minus 0 which is 0, 13 minus 8 which is 5. Other rows remains unchanged 0 1 0 1, 0 0 1 minus 1, 8 and 5, they remain unchanged as it is. Now, the other one, next row, the second row, we have minus 1, that is the first non-zero element. We will have to convert that minus 1 into 1. So, let us multiply the second row by minus 1. So, R 2 is replaced by minus of R 2. 1 1 0 0 augmented with 8. The second row we have just multiplied by minus 1. So, 0 1 minus 1 0 minus 5. The other two rows remains unchanged. 0 0 1 minus 1 5. Now, we have 1 and 1 on the first and second row, sorry, first and third row on the second column. So, let us convert them into 0. So, R 1 is replaced by R 1 minus R 2. Similarly, R 3 is replaced by R 3 minus R 2. R 1 minus R 2. So, 1 minus 0 which is 1, 1 minus 1 you have 0, 0 minus minus 1 you have 1, 0 minus 0 you have 0, 8 minus minus 5 you have 8 plus 5 which is 13. Second row remains as it is. Third row is replaced by R 3 minus R 2, 0 minus 0 you have 0, 1 minus 1 you have 0, 0 minus minus 1 you have 1, 1 minus 0 1, 8 minus minus 5 which is 8 plus 5 you have 13. Last row remains as it is. Now that you have 1 over here, so let us convert the other elements which are 1, minus 1 and 1 into zeros. R 1 is replaced by R 1 minus R 2, R 2 is replaced by R 1 minus R 3, first one, second one R 2 is replaced by R 2 minus R 2 plus R 3, third one R 4 is replaced by R 4 minus R 3, first one, first row is R 1 minus R 3, 1 minus 0 you have 1, 0 minus 0 you have 0, 1 minus 1 you again have 0, 0 minus 1 you have minus 1, and finally 13 minus 13 you have 0. Second one R 2 plus R 3, 0 plus 0 you have 0, 1 plus 0 you have 1, minus 1 plus 1 it is 0, 0 plus 1 you have 1, minus 5 plus 13 you have 8. Third row remains as it is, 0 0 1 1 13. Last row it is R 4 minus R 1, 0 minus 0 0, 0 minus 0 0, 1 minus 1 it is 0, minus 1 you have minus 2, 5 minus 13, so you have minus 8. You have minus 2, so let us convert it into 1. R 4 is replaced by minus 1 by 2 times R 4, 1 0 0 minus 1 and 0, 0 1 0 1 8, 0 0 1 1 13, 0 0 0 1 and you have a 2, sorry you have a 4, because minus 8 by minus 2 you have 4. So, let us convert the other elements in the last column which are 1 1 and minus 1 into zeros. R 1 is replaced by R 1 plus R 4, R 2 is replaced by R 2 minus R 4, R 3 is replaced by R 3 minus R 4. Now, let us do these operations. 1 minus 0 1, 0 minus 0 0, 0 minus 0 0, sorry 1 plus 0 it is 1, 0 plus 0, 0 plus 0, minus 1 plus 1 it is again 0, 0 plus 4 you have 4, second one R 3 R 2 minus R 4, so 0 minus 0 0, 1 minus 0 1, 0 minus 0 it is 0, 1 minus 1 it is again 0, 8 minus 4 you have 4, 0 minus 0 you have 0, 0 minus 0, 1 minus 0 1, 1 minus 1 you have 0, 13 minus 4 you have 9. The last row remains as it is, 0 0 0 1 and you have 4. Thus, the solutions that we have are the following: A equal to 4, B equal to 4, C equal to 9 and D is 4. This is the solution. Now, let us do the second problem. Solve the system x minus 3y plus 2z equal to 0, 2x minus 5y minus 2z equal to 0, 4x minus 11y plus 2z equal to 0. Let us write down the solution to this. Let us first write down the augmented matrix: 1 minus 3 2, 2 minus 5 minus 2, 4 minus 11 and 2. Now, let us try to convert this into its RRE. R 2 is replaced by R 2 minus 2 times R1, R3 is replaced by R3 minus 4 times R1. Let us do the following operations. The first row remains unchanged. The first column will have zeros. Now, let us do the things. Minus 5 minus 2 times minus 3. So, you will have minus 5 plus 6. So, you will have 1 minus 2 minus 4, you will have minus 6 minus 11 plus 12. So, you will have 1 2 minus 8. So, you will have minus 6. Now, let us convert minus 3 and 1 into 0. R1 is replaced by R1 plus 3 times R2 and R3 is replaced by R3 minus R2. The first column remains unchanged. Similarly, the second column you can notice that it is going to be 0 1 0, R1 2 plus 3 times minus 6, which means 2 minus 18, you will have minus 16 minus 6, and last one R3 minus R2 minus 6 minus minus 6, you will have 0. Now, notice that you have a 0 column and therefore, rank of the coefficient matrix only 2. So, we have independent and dependent variables. So, now you do not have a 1 or the leading coefficient in the last variable. So, we will treat the last variable, that is z is the independent variable. So, let z equal to lambda. So, the first equation that we have, let us write down x minus 16 times z is 0, which means x is, this will imply that x equal to 16 times lambda. The second one will give me y minus 6 z is 0, that will imply that y equal to 6 times lambda. Therefore, the solution is the following: 16 lambda, 6 lambda, lambda with lambda n r. Right? These are all the solutions, which means that this system has got infinite number of solutions. Now, let us do the next problem. Solve the system t minus u plus 2v minus 3w equal to 9, 4t plus 11v minus 10w equal to 46, 3t minus u plus 8v minus 6w equal to 27. As usual, let us start with writing the augmented matrix solution. The augmented matrix is 1 minus 1, 2 minus 3 augmented with 9, 4 you have 0, 11 minus 10, 46, 3 minus 1, 8 minus 6 and 27. Now, let us try to convert this into its RRE. You have 1, so let us not bother. You have 4 and 3, let us convert them into zeros. R2 is replaced by R2 minus 4 times R1, R3 is replaced by R3 minus 3 times R1. Let us do the following operations. The first row remains unchanged. second row you have 0, R2 minus 0 minus 4 times minus 1, which is 0 plus 4, you have 4. 11 minus 2 times 4, which is 11 minus 8, you have 3, minus 10 minus 4 times minus 3, which means minus 10 plus 12, you have 2, 46 minus 4 times 9, which means 46 minus 36, you have 10. Next one, R3 minus 3 times R1, which will give me 0 here. Next one, minus 1 minus 3 times minus 1, which is minus 1 plus 3, you have 2, 8 minus 3 times 2, which is 8 minus 6, which will give me 2, minus 6 minus 3 times minus 3, which means minus 6 plus 9, which will give me 3, 27 minus 3 times 9, which will give me just 0. I have 4, let us divide this by 4, R2 is replaced by 1 by 4 times R2, first row remains unchanged, second row I am dividing it by 4, 0, 1, 3 by 4, half, 10 by 4, which is 5 by 2, last row remains unchanged. Let us convert the other elements, which are minus 1 and 2 into zeros. R1 is replaced by R1 plus R2. Similarly, R3 is replaced by R3 minus 2 times R2. You have 1 0 0, 0 1 0. Now, let us do the remaining things. 2 plus 3 by 4, which means 11 by 4, minus 3 plus half, which will give me minus 5 by 2, 9 plus 5 by 2, which will give me 23 by 2. Second row remains as it is, 3 by 4, half, 5 by 2. Last row, R3 minus 2 times R2. So, 2 minus 3 by 2, 2 times, so 2 minus 2 times 3 by 4, which will give me 2 minus 3 by 2, which will just lead to half, 3 minus 2 times half, which is 3 minus 1, which will give me 2, 0 minus 2 times 5 by 2, which will give me minus 5. So, now that we have just half here, let us convert it in, let us multiply this row by 2 and make it into 1. R3 is replaced by 2 times R3, the first 2 rows remains unchanged. Zero, 0, 1, 4, minus 10. Let us convert the other elements 3 by 4 and 11 by 4 into zeros. R1 is replaced by R1 minus 11 by 4 times R3, R2 is replaced by R2 minus 3 by 4 times R3. The first 3 columns are just going to be 0 1 0 0, 0 1 0 and 0 0 1. Now, let us try to manipulate the remaining columns. Minus 5 by 2, minus 11, because you have 11 by 4 into 4, which is just 11, 23 by 2, minus 11 by 4 into minus 10. So, you will have plus 55 by 2, second row half minus 3 by 4 into 4, which will just give me 3, 5 by 2 minus 15 by 2, the last row remains as it is. Now, let us compute these. The resulting matrix is 1 0 0 0 1 0 0 0 1 minus 5 by 2 minus 11. So, you have minus 27 by 2. Next one minus 5 by 2 4. This is 78 by 2, which is just 39, minus 10 by 2. So, you have minus 5, last one is just minus 10. In the last column there is no 1. So, let us call it as the independent variable, that is W is the independent variable. So, let W equal to lambda, and therefore, the first equation will give me t minus 27 by 2 times W is just 39. That will imply that t is 27 by 2 times lambda plus 39. Second one, u minus 5 by 2 times W is just minus 5. That will imply that u is 5 by 2 times lambda minus 5. V plus 4 times W is minus 10. That will imply that V is minus 4 times lambda minus 10. Therefore, the general solution is 27 by 2 times lambda plus 39, 5 by 2 times lambda minus 5, minus 4 lambda minus 10 and lambda, with lambda being any real number. Let us do one more problem on the similar lines. Solve the system x plus 2y plus 3z equal to 1, 2x plus y plus 3z equal to 2, 5x plus 5y plus 9z equal to 4. Solution. Let us begin by writing the augmented matrix 1 2 5 2 1 5 3 3 9 augmented with 1 2 and 4. Now, let us try to convert these two elements 2 and 5 into 0, because the first element is just 1. R 2 is replaced by R 2 minus 2 times R 1, and R 3 is replaced by R 3 minus 5 times R 1. The first row is going to be just 1 0, first column is going to be just 1 0 0. Right. Second column R 2, which is 1 minus 2 times 2, which is 1 minus 4. First column, first row remains as it is 2 1 2 3 and 1. So, 1 minus 4, which will give me minus 3, 3 minus 2 times 3, which is 3 minus 6, which will give me minus 3, 2 minus 2 into 1, which is 2 minus 2, which will give me 0. Now, R 3 minus 5 times R 1, 5 minus 5 into 2, which is 5 minus 10, which will give me minus 5, 9 minus 5 into 3, which is 9 minus 15, that will give me minus 6, 4 minus 5 into 1, which will give me 4 minus 5, which is just minus 1. So, I have a minus 3, let us divide it by minus 3. R 2 is replaced by minus 1 by 3 times R 2. First row remains as it is 1, 2, 3 and 1, 0, 1, 1, 0. Last row again remains the same 0, minus 5, minus 6 and minus 1. Now, let us convert this 2 and minus 5 into zeros. R 2 is replaced by R 1 is replaced by R 1 minus 2 times R 2 and R 3 is replaced by R 3 plus 5 times R 2. So, the first and second column are going to look like 1 0 0 and 0 1 0. Now, let us do the same set of operations on the third and fourth column. R 1 3 minus 2 times 1 which is 3 minus 2 which will give me 1, 1 minus 2 times 0 which is 1 minus 0 which I will have 1, second row remains as it is, R 3 plus 5 times R 2 minus 6 plus 5 into 1 which is minus 6 plus 5 which will give me just minus 1, the last one is just minus 1. Now, let us convert this minus 1 into 1. R 3 is replaced by minus R 3, therefore, I will have 1 0 1 1 0 1 1 0 0 0 1 and 1. Now, let us convert this 1 and 1 into zeros. R 1 is replaced by R 1 minus R 3 and R 3 is replaced by R 3 minus R 2 minus R 3. We have the identity matrix 1 0 0, 0 1 0 and 0 0 1. Finally, 1 minus 1 that is just 0, 0 minus 1 you have minus 1 and 1. Right. Thus, the solutions are x equal to 0, y equal to minus 1 and z equal to 1. This is the solution. Now, let us do one more problem. So, let us try to solve the following system. Solve the system x plus I y equal to 0 minus I x plus z equal to 0 and y minus z equal to 0. You can notice that this is a system with complex coefficients. This is a system with complex coefficients. Let us write down the augmented matrix 1 I 0 minus I 0 1 0 1 minus 1. Right, this is the matrix. Now, let us try to convert this into its RRE. R 2 is replaced by R 2 plus I times R 1. The first row remains as it is 1 I 0. Here you have zeros and zeros. Now, second one 0 plus I times I which is I square you have minus 1. Next one remains as it is, last row remains as it is. Now, let us try to convert this minus 1 into 1 just by multiplying the second row by minus 1. R 2 is replaced by minus of R 2, we will have 1 I 0 0 1 minus 1 0 1 minus 1. Let us convert this I and 1 into zeros. R 1 is replaced by R 1 minus I times R 2 and R 3 is replaced by R 3 minus R 2. So, the first and second column are going to look like 1 0 0 and 0 1 0. Now, let us do the remaining calculations. R 1 0 minus I times minus 1, which will just give me I. Second row remains as it is, third one is going to give me 0. So, you have a 0 row, which means that the rank of this coefficient matrix is just 2, and therefore, you have an independent variable, and so the independent variable is just the last one, which is z variable, because there is no pivot element. So, z is the independent variable. So, what I have now, let us write down z as lambda. Now, let us write from the equations, write down from the equations x plus I times z is 0, that will give me x is minus I lambda. Second one, y minus z is 0, that will give me y equal to lambda. Therefore, the solution set is given by minus I lambda, lambda, lambda with lambda in R, which means you have an infinite number of solutions. Let us look at one more problem. Determine the values of lambda and mu for which the system x plus 2y plus 3z equal to 6, x plus 3y plus 5z equal to 9, 2x plus 5y plus lambda z equal to nu has number 1 no solution, number 2 unique solution, and number 3 infinite number of solutions. Right. So, you are given the system with two unknowns lambda and mu. So, you will have to find the values such that this system has got no solution, unique solution, and infinite number of solutions. Let us try to write the augmented matrix 1, 2, 3, 6, 1, 3, 5, 9, 2, 5, lambda. This is the matrix. Let us do the following operations. R1 is replaced by R3 minus 2 times R1, and R2 is replaced by R2 minus 2 times R3 minus 2 times R2. So, that what you will have, so R3 minus 2 times R1. So, 2 minus 2 into 1. So, you will have 0, 0, 2. Let us compute the other one. 5 minus 2 into 2, which is 5 minus 4, you will have 1. 5 minus 3 into 2, which is 5 minus 6, you have minus 1, 5. Lambda minus 3 into 2, which is lambda minus 6. Lambda minus 5 into 2, which will give me lambda minus 5 into 2, which is 10. Last one is just lambda. Last one, mu minus 2 into 6, which is mu minus 12, mu minus 9 into 2, which is mu minus 18, and then you have mu. Now, let us replace R1 by R 1 plus R 2 first column is 0 0 2 and then you have 0 minus 1 5 this plus this. So, what you will have is lambda minus 16 lambda minus 10 lambda. If you add, sorry, you have 2 lambda minus 16, you have 2 mu minus 30, mu minus 18. Now, let us write down the first one, 2 lambda minus 16 times z is 2 mu minus 30, or equivalently lambda minus 8 times z equal to mu minus 15. Now, let us consider the following cases. Case 1, if lambda equal to 8 and mu in any real number minus just 15, then what will happen? You can notice that if lambda is 8 and mu in r minus 15, which means you have 0 over 0 in the first row pertaining to the coefficient matrix, but there is going to be a non-zero term on the right hand side, which means the system has no solution. System has no solution. Second one, if lambda is not equal to 8, which means this term is a non-zero quantity and mu is any real number. Once you have a non-zero quantity, right, whenever lambda is not equal to 8, you can notice that all the 3 terms are non-zero, which means that the coefficient matrix has full rank, and for any mu you can always notice that this system also has got rank 3, and therefore, the system has a unique solution and finally, if lambda equal to 8 and mu equal to 15, if both these cases arises, which means the first row completely becomes 0. In this case, the system has infinite number of solutions. Right, you have this much. First case is lambda equal to 8 and mu any real number apart from 15. In this case, the system has no solution. Second case, lambda not equal to 8 and mu any real number. In this case, the system has a unique solution. And the last case, when lambda equal to 8 and mu is 15, in this case, the system has infinite number of solutions. Now, let us proceed towards next problem. If the system x plus a y equal to 0, a z plus y equal to 0 and a x plus z equal to 0 has infinite number of solutions, then find the value of a. Solution. Let us try to write down the coefficient matrix, because you have only the zeros on the right hand side, 1 a 0, 0 1 A 0 1. This is the coefficient matrix. Let us try to convert them into its RRE. Before converting, notice that if A equal to 0, then the system has a unique solution, which is just 0, right, because if A is 0, what you will end up with is just the identity matrix. Therefore, in this case the solution is just 0 0 0, but what we wanted is the value of A for which the system has got infinite number of solutions, and therefore, A is equal to 0 is not allowed. So, let us assume that A not equal to 0. Now, let us try to convert it into its RRE. R3 is replaced by R3 minus A times R1. The first row column is 1 0 0, first row in fact remains unchanged, even the second row A 0 1 A, third one 0 minus A times A, you will have minus A square, 1 minus A times 0, you have 1. You have 1. So, let us convert the other two elements A and minus A square into zeros. R1 is replaced by R1 minus A times R2, and R3 is replaced by R3 plus A square times R2. First row 1 A minus A, you have 0, 0 minus A square. So, you have minus A square, second row remains as it is, third row 0 minus 0, 0, 1 plus A square into A, which is 1 plus A cube. Now, for the system to have infinite number of solutions, what is expected is at least one 0 row. Now, you have two zeros. For the last term to become 0, you need 1 plus A cube to be 0, which means A cube should be minus 1. So, what we expect is 1 plus A cube to be 0, because for the other two rows you already have an 1. So, you have a non-zero term. So, which means you cannot expect them to be to become a 0 row. So, only thing that you can expect is the last one. You already have two zeros. So, last term, which is 1 plus A cube, that can become 0. If that becomes 0, that will imply that A cube is minus 1, that is A equal to minus 1. So, if A equal to minus 1, the system, the coefficient matrix has got rank 2. Therefore, the system has infinite number of solutions if A equal to minus 1. Before we proceed to the next one, let us define what is known as definition. A square matrix A is said to be orthogonal if A transpose equal to identity, right. If whenever you multiply A with its transpose, then what you should end up with an identity matrix. If such a thing happens, then you say that such a matrix is an orthogonal matrix. Now, the next problem is if A equal to 0 alpha alpha 2 beta beta minus beta gamma minus gamma gamma is an orthogonal matrix, then find the values of alpha, beta and gamma. Let us try to solve this. What we have is A transpose equal to identity. Let us write down 0 alpha alpha 2 beta beta minus beta gamma minus gamma gamma when multiplied with 0 alpha alpha. Now, I am writing it row wise 2 beta beta minus beta gamma minus gamma gamma. When you multiply these two, what you should end up with is the identity matrix 3 by 3 identity matrix 1 0 0 0 1 0 and 0 0 1. Fine. Now, let us multiply the matrices that are on the left hand side 4 beta square plus gamma square 2 beta square minus gamma square minus 2 beta square plus gamma square. Sorry, second column 2 beta gamma 2 beta square minus gamma square alpha square plus beta square plus gamma square alpha square minus beta square minus gamma square, last one minus 2 beta square plus gamma square alpha square minus beta square minus gamma square alpha square plus beta square plus gamma square. This should be same as 1 0 0 0 1 0 0 0 1. Now, let us write down the equations 4 beta square plus gamma square equal to 1, second one 2 beta square minus gamma square equal to 0, third one. So, this is same as the second, the fourth one is again same as this, next one alpha square plus beta square plus gamma square should be 1, alpha square minus beta square minus gamma square should be 0. These are the 4 equations that I have. Now, let us try to solve them. Let us first write down in the form of a augmented matrix. So, here we have 4 equations with alpha square, beta square, gamma square as the variables. So, 0, 4, 1 augmented with 1, 0, 2, minus 1, 0, 1, 1, 1, 1, 1, minus 1, minus 1 and 0. This is what we have. Let us try to convert them into its RRE. So, what we will rather do is we will swap R1 and R3 and similarly we will swap R2 and R 4. You have 1 1 1 augmented with 1 and then 1 minus 1 0 and then you have 0 4 1 1 0 2 minus 1 0. Now, let us convert them into, let us convert this 1 into 0. R 2 is replaced by R 2 minus R 1. First row remains as it is. Second row R 2 minus R 1, you have 0 minus 1 minus 1 which is minus 2, again minus 2, 0 minus 1 which is 1. Third and fourth row remains as it is. R 2 minus 0 minus 1, you have minus 1 over here. Now, let us convert this minus 2 into 1. R 2 is replaced by 1 by minus 2 times R 2. The first column remains unchanged, first row also remains unchanged. Second row you have 0 1 1 and then half. Third and fourth remains unchanged. Now, let us convert this 1 4 and 2 into zeros. R 1 is replaced by R 1 minus R 2. Similarly, we have R 3 is replaced by R 3 minus 4 times R 2. R 4 is replaced by R 4 minus 2 times R 2. Let us compute all these things. R 1 minus R 2, first column remains 1 0 0, second column 1 0 0 0, second column 0 1 0 0. Now, let us do the other one. R 1 minus R 2, you have 0 1, R 3 1 minus 4 times R 2, which means 1 minus 4 you will have minus 3, minus 1 minus 2 times R 2, which will just give me minus 3. Again R 1 minus R 2, 1 minus half, which will give me half, second row is just half, third row R 3 which is 1 minus 4 times half, which is 1 minus 2, which will give me minus 1, sorry 1 minus 2, 1 minus 2, minus 1, 0 minus 2 times half, which will give me minus 1. Let us convert this minus 3 into 1. R 3 is replaced by 1 by minus 3 into R 3. So, you have 1 0 0 0, 0 1 0 0, 0 1 1 minus 3, and then you have half half 1 by 3 minus 1. Let us convert this 1 and minus 3 into zeros. R 2 is replaced by R 2 minus R 3. R 4 is replaced by R 4 minus R 4 plus 3 times R 3. 1 0 0, 0 1 0 0 0 1, and then you will have 0 0 0. Let us compute the last column. R 2 minus R 3, sorry, first one is just half, R2 minus R3. So, 1 by 2 minus 1 by 3, which will end up with 1 by 6, 3 minus 2 which is 1 by 6, and then you have 1 by 3, last one is going to be 0. Now, let us write down the solution. So, the solution in this case is alpha square is 1 by 2, beta square is 1 by 6, and gamma square is 1 by 3. Thus, the values of alpha, beta and gamma are alpha equal to plus or minus 1 by root 2, beta equal to plus or minus 1 by root 6, and gamma equal to plus or minus 1 by root 3. Right. So, these are all the values of alpha, beta and gamma for which the given matrix becomes an orthogonal matrix. So, with this let me stop. Thank you all.